Hi, hello, good day, and welcome to the video on relations and functions. Can you guys tell that I've had a lot of coffee today? Okay, so we're going to talk about relations and functions. So first, let's define a relation. A relation is a set of ordered pairs. Okay, tells us that right there. And it can be shown in a table, a graph, a mapping, or expressed as an equation. Now, we are going to look at examples of all of those, so don't freak out if you don't know what I'm talking about, okay? Right now, let's just take some notes, and then we'll get to know what a relation and a function is a little bit better as we go on. Okay, so the set of x values, because remember these are ordered pairs. Ordered pairs are x comma y, and they tell you where to plot a point on a coordinate plane. All right, the set of x values is called the domain, and the set of y values is called the range. Domain and range, that's something I'm sure you've heard of before. A relation with distinct points is called discrete, and a relation with connected lines or curves is called continuous. So if it was discrete, think of like a scatter plot where you have dots like that. And if it were continuous, that's when I think of like the XY plane with a graph on it. Okay, this would be a continuous function. So a function is a type of relation. It's a relation in which each element of the domain, so remember domain are the x's, is paired with exactly one element of the range. Range is the y's. So this is one way of writing a set of ordered pairs. We use a bracket to identify that it's a set, so we'll have two brackets, and then each ordered pair is in parentheses. So I'm just going to write out an example here for you. All right, so a function, if you can pause this and write those down. I paused it so the video wouldn't be as long. In a function, that means the x values do not repeat. That is a simple way of saying what this is saying, is that the x values don't repeat. So if you look at the example that is a function, we have 0, -5, 6, and 5. Those are our x values in each of our coordinates. And then so none of those repeat. This is a function. On our not a function example, we have -7, 6, 6 again. So this is our problem x value. And then we have -3. But this 6 can be associated with -1 or +2. And that's what makes it not a function. And something I forgot to say in the last section, whenever we wrote it with a bracket and like a list of coordinate of ordered pairs, that is representing the relation just as a set of ordered pairs. So that was the first part of our definition of a relation, was a set of ordered pairs, and that's one way of writing them. So we said that a relation can also be represented by a graph. Okay, so if you look at your list of ways that we can look at a relation, graph is one of those. So the vertical line test is a way to tell us if a relation is a function. So I'm just going to use an example of a relation that would be a function is a line like this. And an example of a relation that would not be a function is a graph of a circle. And I'm going to show you with the vertical line test how this works. So imagine that I drew a vertical line through my function, anywhere that you want. It only crosses this function at one point, okay? And anywhere that we draw this vertical line, no matter where you put it on this function, there is nowhere you can put it that it will hit your function more than one time. That is how you use the vertical line test to tell us that this is, in fact, a function. Okay, in order to be a function, a vertical line cannot pass through more than one point in the relation. Okay, and if you look at the example that is not a function, if I draw a vertical line through this, then it crosses twice. And so that tells me that this cannot be a function. That is how the vertical line test works. And a way that you can do that whenever you are sitting down and working on your papers is you can lay your pencil down as if it were a vertical line and slide it across your graph. And if at any point your pencil crosses the relation more than once, then that means it cannot be a function. So let's do a practice problem here. We're going to talk about domain and range, and we're going to decide if these are functions. So again, this relation is listed in the form of a set of ordered pairs. So when you see these squiggly brackets, that means a set of something. And then when you have parentheses with two things in the middle with commas, that's almost always an ordered pair. So these are your x's and these are your y's. X and y, x and y, x and y. You probably learned this before whenever you learned how to graph equations and graph things on a coordinate plane. So our domain is going to be written as a set of numbers, but instead of ordered pairs, we only need the x values. So there's one, there's one, there's one, and there's one. So this, and you list them in order of their value, so not always left to right. Okay, in this case, they are in order left to right from least to greatest. So we have -1, 0, 4, and 6. That is our domain. Now our range consists of these numbers. And if you notice, this -2 is not in order. It should go between -5 and 3 whenever we make our list. When we write our set for the range, we put these in order from least to greatest. So -9, -5, -2, +3. Okay, so they don't necessarily match up with the x's in order. And that's okay because we want them in order from least to greatest. Now, is this a function? If you recall, in order for a relation to be a function, the x values cannot repeat. So we have -1, 0, 4, and 6. None of those are the same. So yes, this is a function. Now this representation of a relation is a table. I'm sure you've seen tables before and you're familiar with them. And this makes it pretty easy for us to find domain and range because our x's are listed here and our y's are listed here. So our domain, and remember we go least to greatest, so we have to start with -4, is -4, 0, 2, and 7. Then our range is all of our y values, again in order from least to greatest. So -8, -1, +3, and +3. Now, whether or not it's a function depends on the x values. So we have a repeated y value, but that does not matter. We don't care about that. We only care about the domain. And in our domain, all 4 pieces are unique. There's no repeating x values. So again, yes, this is a function. So for number 5, this representation of a function is called a mapping. And it's because it maps out which pairs go together. Okay, so in our list of ways that relations can be represented, this is an example of mapping. And it's kind of similar to a table, but you'll notice that this 5 has 2 different things that it can be matched up to. So when we list our domain, we're going to have -4, -2, and 5, but we have to list that 5 twice because it's used twice. And then our range is going to be 0, 3, 7, 9. And remember, we used the number 5 twice in our domain, so this is not a function. Number 7 shows us another relation, and in this one, this is represented by a graph. So what we're going to do is list everything in our domain. So we're going to go along we care about where these fall on the x-axis. So we have this point here, and that falls at -3. And if you work left to right, then they will be in order from least to greatest. So we have another point at -3, and then we have this point that falls at 0 on the x-axis. And then we have this point that falls at +2, and this point falls at +4. So now let's list our range. And on the range, we care about the y-axis and where it falls vertically. So now we're going to start from bottom to top. That way we have them in order from least to greatest. So this point is at -5. This point is at -2. This point is at -1. This one is at +1. And this one is at +4. And we want to know, is this a function? And right here we have 2 of the same x value, so no, it is not a function. And another thing that we could observe is that if we used a vertical line test and we drew that vertical line right here, it would cross 2 points at the same time. And so that also means this cannot be a function. Number 9 shows us another graph. But if you remember, whenever we talked about types of relations, there are continuous relations and discrete relations. So number 7 was a discrete relation where it had distinct points. But this is a continuous relation because it consists of continuing lines. So not only is, this point part of the relation, but so is this point and 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 every little minuscule point in between. So that's why it's called continuous, because there's really infinite number of points that are included in this. So if there are an infinite number of points, then how in the world are we supposed to decide what the x values are and what the y values are? So the best way that I've figured out to explain domain and range whenever you have a graph like this is, so domain is what x values actually get used in this function, okay? So I like to explain it as if you were taking 2 bars and you're going to squish them together and see what your function would turn into. So here's our function. And when we squish it vertically onto the x-axis, that's going to look like it's going to start here because that's the furthest point to the left. And these arrowed points are going to squish down to here, and we'll have an arrow that points that way, and this bottom one will come up and we'll have an arrow way out here. So what this tells me, this is now kind of like looking at an inequality graph. Okay, so we see that x can be -4, but it can't be anything smaller. And we have arrows pointing this way, so that means our x values go all the way to infinity. So we're going to write the domain as an inequality, and it's going to be x is greater than or equal to -4. And that tells us that any x value that's less than -4 does not get used in our function. Our function ends right here. But now it has arrows that go towards the right, which means it's going to go forever this direction. Okay, that's a lot of scribbles. I know that was a lot. I'm sorry. But so now let's look at the range. The range is the y values. So we care about this axis. And we want to think about squishing our graph into the y-axis. Okay, so we're going to squish this in, and what's going to happen is that this part of the graph is going to come in and it's going to go this way, and that arrow is going to point up, and this part of the graph is going to get squished in and it's going to point that arrow down. And so now we have arrows pointing up and down, and there's no gap in between. Okay, there's no value of y where it doesn't match up to somewhere on our graph. And so what that means is that our domain or our range is all real numbers. And that's the symbol for all real numbers that you've learned about before. And you could also say, as an inequality, that negative infinity is less than or equal to x is less than or equal to positive infinity. And that just says that x is all real numbers. This is the easier way to write this. So now our question is whether or not this relation is a function. And so we will take the vertical line test and see if a vertical line is it possible at all to draw a vertical line that will cross our graph at 2 points. And over here, it doesn't really look like it, but over here in this area, it does cross twice. So this is not a function. Now for this one, we actually have to create the graph ourselves. And so I'm going to show you a calculator that you can use online if you don't have a graphing calculator, and it's called Desmos. And to get to that, you're going to use this web address, desmos.com/calculator. You can also just Google Desmos calculator and it will come right up. It's very easy to find. So I'm going to switch you over to that and show you how to find domain and range and decide if it's a function for this problem and for number 13 as well. And so when you do the even numbers 12 and 14, you'll do those using either your own graphing calculator or this online graphing calculator. Okay, so number 11, this is what Desmos should look like whenever you pull it up. And number 11, our function is y equals negative x squared, and you'll see how this is graphing something as we go, plus 3. So once you have this all entered, it will show you the graph. And as you're typing on your Chromebook, you may find it easier to use this keyboard that Desmos provides. It's got more calculator type symbols on it. So it might take you a minute to kind of figure out how to do everything on it, but you can use that keyboard or you can type straight into the thing with your own keyboard. Okay, so in order to decide if this is a function or not, we need to find domain and range. So remember that domain is your x values. So we want to find D. And we do that by looking at the x-axis. because that's what we care about right now. And keep in mind that where this graph goes off the screen, you need to treat those as arrows, okay? So that goes forever that direction and forever that direction. So remember, if we use our two bars and we squish our function onto the x-axis, then our function, like this part's going to come down, and so we'll kind of have the vertex here, or the curve, whatever you want to call it. And then these arrow parts, they're going to stretch out this way and this way. And so do we see that as we squish these lines in toward the x-axis, how this curve is going to get flatter and flatter and flatter until it becomes a straight line? And this line encompasses the entire x-axis and has arrows on both ends. It doesn't have a finite point. And so that means that our domain is all real numbers. Any value of x whatsoever will at some point hit our function, because even though it looks like that maybe our x's stop here, these are going slightly to the right. So like if I come way out here where x is equal to -10, it's going to take a really long time to get down there to where it actually crosses this function, but eventually somewhere way off of the screen, those will intersect. So let's look at the range now. Remember that the range is the y values, and so we are concerned with the y-axis. And we're going to do the same thing as we did with the x-axis. We're going to squish our function between these two lines. We're going to squish it in. If you could see my hands, you would see me squishing things. And close it in on the y-axis. And so our function, this little point, it's not going to go past there because that's where there's nothing over here to squish. But these are going to squish straight onto, both of them will be right here on the y-axis. And remember, these are arrows, and so this will still be an arrow going down. So the biggest number that our y value can be is whatever this point is. And I'll erase all this so we can see what that is in a minute. Actually, we don't have to. This is labeled 2, labeled 4, so that in the middle is 3. So that's +3. So we know that y has to be less than, because it's going down, less than or equal to +3, because it goes through +3, so it can also equal +3. That's your domain and range for this function, or, well, relation. We don't know yet if it's a function. So now we have to do our vertical line test. So is it possible to draw a vertical line that will cross our graph more than once? So if you just start putting lines in here, there is nowhere on this graph that you can possibly draw a line vertically that will cross it more than once. So that means that this is a function. So now let's graph number 13. Y equals -7. And you can see at the bottom of the graph that it's just a straight line through the value -7. So let's think about what our domain and range will be. Domain is our x values. So if we were to squish this line up to the point that it would lay on the x-axis instead of where it is, it's still going to be a straight line, and it's still going to go forever in both directions. So that means that the domain is all real numbers. However, whenever we look at the y-axis, when we look at our range, and we squish our function in this direction, it's all going to compress to one single point. on the y-axis because it doesn't go through diagonally. It's not going to get squished to here. It's a straight, perfectly straight line. So both sides are going to push straight perfectly into this point. And so our range is only the value y equals -7. Now, I want to give you an example of what would happen if this were a vertical function. So I'm also going to give you an example of a vertical function, or a vertical line function. So here I've shown you the function x equals 3, and that has created a vertical line. So our domain, remember, if we squish things into the x-axis, then our domain will all fall in one point, which is going to be x equals 3. But our range will fall on the entire y-axis, so your range would be all real numbers. But the question I'm concerned about here is whether or not this is a function. And I didn't answer that question in the last one. Wow, way to go, Ms. Schwartz. So back to whether or not number 13 is a function. If we draw vertical lines through this anywhere that we want to, it is impossible to hit it in more than one place. So yes, this is a function. So now let's go back to the vertical line and discuss whether or not this is a function. So, you know, any vertical line that we draw out here trying to do the vertical line test isn't going to touch our function at all. But what if we draw a vertical line right here? And I realize that that's not perfectly straight, so it kind of defeats the purpose. But pretend that that is exactly on top of our function. Let me try a little harder on that. Oh, look at that beautiful line. Okay, so what if that vertical line is the line that we use to test whether this is a function? That vertical line touches an infinite number of points on our function. It touches all of them at once. So that is crossing the function more than once. Okay, so that's a little bit of a abstract way of looking at that. And so I wanted to make sure I covered a vertical line with you all because vertical lines do not pass the vertical line test and are not functions. All right, that's all I've got for you for this video. Thank you for watching.